Hello and welcome to the next of these chats, this time introducing the often confusing topic of decibels. We'll start with the definition. A decibel is 1/10 of a bell, named after Alexander Graham Bell. A bell is a logarithmic unit. It is defined as the log to the base 10 of a power ratio. So, for example, you can express the gain of a system in bells. The power ratio would be the output power divided by the input power. Just take the log of that to the base 10 and you get the answer in bells. A decibel is 1/10 of a bell in the same way that a decimeter is 1/10 of a meter and a deciliter is 1/10 of a litre. The deci, SI prefix, is not as commonly used as the milli prefix, meaning 1,000th, or the centi prefix, meaning 100th, but it is a standard, and a decimeter is 10 centimeters long, 1/10 of a meter. A decibel is 1/10 of a bell. So just like a meter is 10 decimeters, and 3 meters is 30 decimeters, and x meters is 10x decimeters, a power ratio of 3 bells would be 30 decibels. You take the value in bells, that's log to the base 10 of the power ratio, and multiply it by 10 to get the value in decibels. That's it. There are two formulas which are fundamental to decibels. These are they. The first one is how to work out the gain in decibels given the power out and the power in. The second one is how to work out the power out in terms of the power in if you were told the gain in decibels. And you can derive one of these formulas from the other one quite readily. Perhaps I should do a quick example. Supposing I had an amplifier which had an output power of 500 watts and its input power was 5 watts. Then the gain of that amplifier would be the output power divided by the input power. I could write the power gain equals 500 over 5, which is 100. And it's dimensionless. It's a power divided by a power. There are no units. If I wanted to express that in dBs, I would take 10 times the log to the base 10 of this power ratio. And that would be 10 times log to the base 10 of 100. Log to the base 10 of 100 is 2. So that just says that the gain of this amplifier in dBs is 20 dBs. I can use the second of those two formulas to work out the output power given the input power. Here we have an input power of 5 watts. So the output power would be the input power, 5 watts, times 10 to the power of the gain in dBs divided by 10. That's 5 times 10 to the power of 20 over 10, which is just 5 times 10 squared, which is 500, as expected. And those are the two fundamental formulas for working with decibels and power gains. So far, everything is quite straightforward. The problem comes when you start applying decibels to voltages. Voltages are not powers. Most of the time, when we're going to be dealing with amplifiers in this module, we're going to be dealing with an amplifier that gives an output voltage corresponding to an input voltage. So we'll have an amplifier like this. It will have an output voltage and it will have an input voltage. And we will want to express the gain of that amplifier in decibels. But we can't, because we don't know what the output power is and we don't know what the input power is. We just know the input and output voltages. So we bodge it. And it's a confusing bodge. And the bodge goes like this. Most of the time, when we look at circuits, the power is proportional to the square of the voltage. For example, the power dissipated in a resistor is proportional to the square of the voltage across that resistor. So we could say, okay, well, if the power is proportional to the square of the voltage, then we could say that the output power must be some constant times the square of the output voltage. And similarly, the input power must be some constant times the square of the input voltage. And therefore, the ratio of the output to the input power must be the square of the output voltage divided by the square of the input voltage, which I could write as the ratio of the output to input voltages squared. Except, this is only true if these two constants are the same. And there's no particular reason why they should be. And indeed, there are quite a lot of exceptions where these two constants are not the same. If you can identify the output power as the power across a resistor and the input power as the power across a resistor, then the output power is actually equal to the output voltage squared divided by the output resistance. And the input power is the input voltage squared divided by the input resistance. And there's no reason that the resistance at the output should be equal to the resistance at the input. So in this case, if I tried to express the output power as a ratio of the square of the input power, I would end up with this formula here. Now that is not equal to 10 log 10 of V out over V in squared. Or at least, in general, it's not. It's only true if R out equals R in. A lot of times, though, it's difficult to identify what resistance is appropriate to use. So, we just ignore the problem and say that all the resistances are just equal to 1, and therefore they cancel out, and we can just use this formula and we're fine. Yeah. It is a bit of a bodge, but it's a very common bodge. It's one that everybody uses. You just have to get used to it. And in circuits where you cannot identify an output resistance or an input resistance, just accept that the way everybody uses decibels is to use this formula. 10 times log to the base 10 of the square of the two voltages. Although, actually, we tend to use the useful property of powers that the log of x squared is equal to twice the log of x, and just write this as 20 log 10 V out over V in. And that is the gain in dB when you know the output and input voltages, but not the output and input powers. The inverse formula is useful to know as well. If I just take both sides of this equation, divide by 20, and then raise them to the power of 10, I end up with 10 to the power of the gain in dB divided by 20 equals V out over V in. And therefore, V out is V in times 10 to the power of the gain in dB divided by 20. Okay, let's do a couple of examples. Here's one to get started. Got a sine wave source which has an input of 0.5 volts, which I could write as 500 millivolts. Goes through an amplifier, and we want to be able to express the gain of that amplifier in dBs. The output of the amplifier is 50 millivolts. What is the gain of this amplifier? Well, we can just directly apply the formula. 20 times log to the base 10 of the output voltage, 50 millivolts, divided by the input voltage, 500 millivolts. That would be 20 times log to the base 10 of 0.1, 1/10. Log to the base 10 of 0.1 is -1, so that would be minus 20 dBs. The fact that this is a negative dB just means that the output is smaller than the input. It happens quite a lot. Now, at this point you might be wondering, why go to the bother of expressing gains in dBs at all? Wouldn't it be much easier just to specify everything in terms of its voltage gain and say this amplifier has a voltage gain of 0.1? Well, the real usefulness of decibels becomes apparent when you have two amplifiers in series. Something like this. And you're told what the gains of those amplifiers are in dBs. And this is where the fact that dBs are logarithmic units really starts to help. Supposing I have an input and my input is X. It goes through an amplifier of gain 10 dBs. The output there would be X times 10 to the power of 10 over 20. These are voltages, which is why I'm using over 20. That goes into the next amplifier, and this amplifier has a gain of 20 dBs. Well, this is the input to the second amplifier, so the output of the second amplifier will be X times 10 to the power of 10 over 20 times 10 to the power of 20 over 20. The input times the voltage gain of this amplifier. And that is X times 10 to the power of 30 over 20, using the property of indices that x to the power of a times x to the power of b is x to the power of a plus b. But this is the output of an amplifier with a gain of 30 dBs, which is the sum of these two gains in dBs. And that is generally true. If I had an amplifier here of gain A dBs, feeding another amplifier of gain B dBs, and I put an input signal here of V in and an output of V out, then the total gain of these two amplifiers together would be A plus B dB. They would work exactly the same as an amplifier which had a gain of A plus B dBs. That is one of the main reasons why people like to use decibels. If you're combining amplifiers like this, you don't have to multiply the gains together, you can just add up the gains in dBs. And adding is much easier to do than multiplying. Okay, that's the end of the quick introduction to decibels. Next time we're going to look at some derived units, some methods of expressing voltages in dBs rather than voltage ratios.